Hi everybody. This is the extreme problem set, the big one, the hard set of four problems. And I actually made a mistake when I was writing it up, so I actually adjusted number four. So if you have done these or you want to do them, I made a couple of changes to number four, so you can actually go back on Edline and re-download and work on four again if you want. Just because the way I had it set, the projectile would never get that high. You end up with a negative answer and it gets weird. So I adjusted it. It works now, and 1 through 4 I'm going to be able to walk you through right now. So again, study this for Tuesday. Um, the big deal about Tuesday is it's going to be basically an exam that's got a couple of multiple choice problems, and then four pretty intensive problems. One that's going to be vector addition, one that's going to be a cliff problem, one that's going to be a launch problem, and then one that's going to be one of these. So hopefully you take advantage of this and you actually work through it. So let's get started going through these. Your group has determined a launch velocity of the marble launcher to be 6 meters per second. You launch a marble with an angle of 70 degrees from the table, and it lands 1.25 meters below where it started. How far away should the base of the table, or how far away from the base of the table will it land? So let's start off the way we always do. Nice little XY chart. VI, VF, ATD. And let's plug in what we know. So we're going to launch the marble with a velocity of 6 meters per second at an angle of 70 degrees. So we should know by now that 6 goes neither in the X or the Y, but it will land 1.25 meters below where it started. So we can actually put negative 1.25 meters below for my displacement in the Y. We also know the acceleration in the X is 0, and the Y is negative 10. And the first little piece of this that we should be good at by now is doing some trig. So we know the initial velocity is 6 meters per second. We also know that, and forgive me, this is not as clear as it looks on the smartboard, but we're going to launch this with an angle of 70 degrees from the horizontal. And to figure out the y component of this, it's 6 sine of 70, and the x component is going to be 6 cosine of 70. And what we should get out of those is 5.63 meters per second in the y dimension. So 5.63 in the y, and we should end up with 2.05 in the x. And you can probably just round that down to 2 in the x, and 5.63 in the y. The final velocity in the x is going to be also 2 meters per second, and the y dimension is going to be we don't know. So that's the first thing we have to figure out, is how fast is this thing going in the y when it gets to where it's going, because once we have the initial velocity in the y and the final velocity in the y, we can actually figure out what the time is. So the way we do that is use the equation VF squared equals VI squared plus 2AD. And we know most of this, just not VF. So VF squared equals VI squared, which is 5.63 squared, plus 2 times negative 10 times our displacement is negative 1.25 meters. And if we add all this together and take the square root, we should end up with a final velocity of plus or minus 7.52 meters per second. So if we're shooting this projectile from the marble launcher up, it's going to be going something like this. That's how it's going to look. So here's the table. Here's the table. You can erase this. It's going to go up, reach a peak, and then come back down and land on the floor. And this height is 1.25 meters. So what's happening is when we get to a certain point, the positive 7.52 meters per second would be if we shot it from down here, but we're landing it over here, so the final velocity is going to be negative 7.52 meters per second. So that's good. We're going to discard the positive. We only want the negative. And the other thing that we can do now is figure out time, which is ultimately what we need. So we'll do VF equals VI plus AAT. VF is negative 7.52 meters per second. VI in the Y will be 5.63 meters per second plus negative 10 times T. And solving for T, we should end up with time equals 1.315 seconds. So that can go here, 1.315 seconds. And now we can do V equals D over T in the X to get, let's see, 2 equals, so V equals D is what we're looking for, over time, which is 1.315 seconds. Multiply both sides by 1.315. We're going to get a displacement of 2.7 meters away. So that's your answer for the first one. Plug it in there. So from here to here should be about 2.7 meters away. So if we were doing this in class, that would be where I put the red cup, if you remember that, or if you were in one of the later classes, the bucket. So I hope that helped. Again, these are the hard problems. So, you know, what we start out with is, you know, basically a quadratic function, and we sort of backhandedly figure out the time without using the quadratic equation. Again, if you want to use the quadratic equation, go for it. I just, you know, I don't like it because there's another way to do it, and it requires a little bit more thinking, but it's good. So hope that helped. Your negative velocity in the Y is going to be 7.52 going down. That'll get you your time, and then you can get your displacement in the X. That's basically the trick for all these. Our next problem is somebody hijacking my potato cannon. I hate when that happens. During the summer, remember that it shoots projectiles with a velocity, we figured this out, of about 45 meters per second. They bring it to Cunningham Pool and shoot it at an angle of 35 degrees to the horizontal. So that's what it's going to look like, 45 meters per second at 35 degrees to the horizontal. So these people are going to fire my potato cannon, and the potato lands on somebody's roof, and it's 15 meters above where it's fired because it lands on a roof. It doesn't come all the way back to the ground. So somehow, some way, we're going to have a displacement in the Y of positive 15 meters. So XY, VI, VF, A, T, D. We're going to plug in positive 15 meters, which is interesting because before we had the thing landing lower by 1¼ meters. So that's why that's negative 1¼ This is landing positive 15 meters above where it's being fired from. So that's just a little interesting tidbit that you should probably pay attention to. 45 goes nowhere in our chart. We're going to use 45 meters per second to figure out the X and Y components. To figure out the Y, it's going to be 45 sine of 35. And figure out the X components, going to be 45 cosine of 35. And those will both give us 36.86 meters per second, and this one will be 25.8 meters per second. 36.6, or sorry, 36.86, 36.86, 0. This guy's going to be negative 10, and this will be positive 25.8 meters per second. And that's really all we know to start this problem out, now that we've got our two initial velocities. Once again, we need to get time. If you want to go for the quadratic equation, you can use d equals vit plus 1/2 at squared and figure out time that way. But you know me, I like using vf squared equals vi squared plus 2ad. All of this stuff is coming from the y dimension because we already know vf in the x, and that's really not going to get us anything useful. So our final velocity we don't know, but our initial velocity we know it's positive 25.8 plus 2 times negative 10 times the displacement, and that's going to be squared. So if we plug all this in and take our square root of the VF, we should end up with a final velocity in the y dimension of plus or minus 19.12. If we remember, this is going to go up and land on somebody's roof coming back down. So we're going to take the final velocity of negative 19.2 meters per second. So that's kind of cool. What's next? Let's see here. We can go ahead with that final velocity and do Vf equals Vi plus At. Final velocity is negative 19.2. I'm sorry, 19.12. 12 equals Vi, which is 25.8 plus negative 10 times T. And time, if we do all of our algebra correctly, should be about 4.5 seconds. So using T, we can now use the equation V equals D over T, solving 36.86 equals displacement over 4.5 seconds, and that will give us a displacement. If we multiply both sides by 4.5, our displacement will be 165.8 meters away. So that's where the house with that roof would be. And sorry, I forgot to put 4.55. I'm sorry, 4.5 seconds is our time. So again, I hope that helped. Hope you got it without that. But if you didn't, that's kind of how you do it. This part will get you your final velocity. This part will get you your time. And this part will get you your displacement. Third problem, Rachel's babysitting a wonderful child, and I use wonderful very sarcastically. I'm sure we've all had small babysitting jobs that you have kids that are just not the nicest of people. Well, we start with an XY, VI, VF, A, T, D. I'm not even going to read the problem. I'm just going to plug in 0 and negative 10. So we're babysitting a wonderful child who has climbed a tree to a height of 10 meters. The child has decided to bring an apple and throw it back at Rachel with a speed of 6 meters per second and an angle of 30 degrees below the horizontal. Rachel's 1.9 meters tall. How far from this kid should she not be standing? So let's take a look at this and we'll figure out the information that's important. Here's the tree and the kids, let's say here, and they're 10 meters above the ground, and Rachel's standing over here, and she is 1.9 meters tall. So if the kid throws the apple from here, it's got to drop that far before it hits Rachel. And if you do that correctly, the tree or the apple is going to fall 8.1 meters down. Okay, we have 10 meters to play with. Rachel's 1.9 meters tall, so the apple would have a chance to fall exactly 8.1 meters. And because we're talking about the apple falling, the apple is the projectile in this question. That's the displacement, negative 8.1 meters. Okay, so that's what we're actually going to use. Also, this kid throws the apple down, so this isn't even really a cliff problem. As I drew it here, my apologies. The kid is going to throw the apple downwards. So kid's up here. Really not a good parabola picture, but I hope you get the idea. We're throwing it downwards. The kid's throwing it down. So what we need to do is figure out what's going on with the initial velocity in the x and the y like we always do, but instead of the hypotenuse being up like that at some angle to the horizontal, this kid's a real bugger, not very nice, and they throw it down like that at an angle to the horizontal, so that angle. And we see in the problem that the angle that they throw it is 30 degrees below the horizontal, and the kid throws it at a velocity of 6 meters per second. So now we've got 6 for a hypotenuse, and we need to figure out what's going on in the x and the y. Once again, we will use 6 cosine 30 to figure out the x and 6 sine 30 to figure out the y, but the big deal with this is once we get this side, we have to remember that it's going downward, so it's actually going to be a negative quantity. So 6 cosine 30 should give us 3 meters per second, and this one is going to give us 5.19 meters per second, and that because that's going down, that's a negative. and that's a positive because I just drew it that we're going to go to the right. So 5.19, 5.19, and then negative 3 meters per second in the x, or I'm sorry, in the y. So we've got all this. Now we need to figure out time, but we don't have enough information really to do it without the quadratic equation. So we can figure out the final velocity and then just go back and use an easier equation to figure the rest of it out, to figure out time. So Vf squared equals Vi squared plus 2AD. Vf squared, we don't know. Vi squared is negative 3 plus 2 times negative 10 times the displacement. Oops. Times the displacement. But we already know the displacement. Negative 10 times the displacement, which is negative 8.1. Now, your calculators might be unhappy with this. I'm not sure how the calculators that you have work, but negative 3 squared in my book is positive 9 plus 2 times negative 10 times negative 8.1. We should end up with an answer that is 162 for this part. So 2 times this should give us 162. Plus 9 means we'll have a final velocity squared of 171. And then we take the square root of 171, and we should end up with a final velocity of plus or minus 13.07. 13, I'm just going to leave it as 13. So, because the apple is being thrown down, we know it's never going to come back up, so we can ditch that positive. So our final velocity in the y dimension is going to be negative 13 meters per second. So now we can go back and figure out our time using Vf equals Vi plus At. Final velocity is going to be negative 13. Vi is going to be negative 3 plus negative 10 times time. 13 plus 3, remember we've got to get rid of this negative 3, so we'll add 3 to both sides. Negative 13 plus 3 will be negative 10, equals 0 plus negative 10t. That would be nice if I crossed the t there. And last time I checked, negative 10 divided by negative 10 is going to give us a t of 1 second. So let's make a 1 second in there. 1 second is our time. And then if we use v equals d over t, I'm not even going to bother to write this down. Our v is 5.19. Our displacement is something, but our t is 1. So 1 times 5.19 is going to give us a displacement of exactly 5.19 meters. So if Rachel doesn't want to get clocked in the head with an apple, she should not be standing exactly 5.19 meters away, because that's where she would get clocked. If she was closer, the apple should go over her head. If she's further away, the apple will hopefully land in front of her. But that's where we don't want her to stand. Hope that made sense. And I really hope that you guys are doing well on these. Next question, last question. This is the one that I actually had to sort of redo because 60 meters per second was not fast enough for the trigonometry to get the projectile to go as high as we needed it to. So I changed it to 70 meters per second, and I also had a typo. I said 130 meters away. It's actually 130 meters high. So that's going to be important for us. Make another x, y, vi, vf, a, t, d. This is a good problem. So we're going to launch this thing. Projectile is launched from the ground with a velocity of 70 meters per second at an angle of 55 degrees above the horizontal. You can make that assumption. Towards a target that is 130 meters high. So let's make a little bullseye here. And the displacement here is 130. D and the y is positive 130. So what's going to happen is this thing is going to go up, 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 and then reach a peak, and then come back down. And that's what I'm saying. If the projectile hits the target on the way down, how far away in the x dimension is the target? So we know the displacement in the y is going to be positive 130. Okay, but if you see, it hits 130 meters on the way up and coming back on the way down. and that's going to be significant to us as we go through the problem. What we've always done is 0 and negative 10, and then our 70 goes neither place here. We have to do 70 sine of 55 and 70 cosine of 55. And we should end up, not 50, 55. And we should end up with a couple of different velocities. The y velocity in the initial is going to be 57 meters per second, and the velocity in the y is going to be about 40 meters per second. So I'm going to go ahead and plug those in, 40 and 40. And this one is going to be positive 57. And we need to figure out time, but again, quadratic formula would be the only way we do it. So I'm going to go ahead and solve for the final velocity and use the easier equations. Vf squared equals Vi squared plus 2AD. Vf squared we don't know yet, equals Vi squared, which is 57, plus 2 times negative 10 times our displacement is 130. Now, this gets to be a very, very big number. But you should end up, if you do 57 squared plus negative 2 times negative 10 times 130, you should end up with Vf squared equaling 649. 57 squared is a huge number. This is a huge number also, but because it's a negative here, we get to subtract this big number from that big number. And the difference should be positive 649. The reason I knew this was wrong before was because I actually ended up with a negative number when it was only 60 meters per second. So we can't take the square root of a negative number. So I changed it to 70 meters per second, which means it went up further, and we ended up with a positive final velocity. From this, we get a square root of this, and we can do Vf will be plus or minus, at this point, 25.5 meters per second. Okay? And because I say it hits it on the way down, our final velocity can't be positive, because if it's going back down in the y dimension, it's going to be having a negative velocity in the y. So negative 25.5. Okay? From there we can do Vf equals Vi plus At. Vf is negative 25.5 in the y equals 57 in the y plus negative 10 times t. And you should, if you do this correctly, end up with a time of t equals 8.2 seconds. So this thing is in the air for a very long time. Okay, and then once we've got that, we can go back to our x. D equals d over t in the x. Velocity is 40 equals d, which we don't know, over 8.2. Multiply both sides by 8.2. Your displacement should end up being 328 meters away. So I hope these three examples sort of got you thinking. Again, if this projectile hit the target on the way up, which is interesting, we'd be talking about it hitting here, which would mean that our final velocity would be positive 25.5 meters per second, which would actually make our time much less, and that would in turn make our displacement much less. So from the launch point to where we place the target, 328, but if it was, and that's when it hits on the way down, but if it was hitting on the way up, the distance from our target to here would be much smaller. Okay, so I hope that helped. I hope you have a wonderful weekend, and go Pats. So I'll see you all on Monday.